discusses a lot about notation. Okay. Yeah, let's not say this. Yeah, let's skip this. We can now verify the equivariance of the Navier-Stokes equations. Okay, and this is going to be, again, a lot about notation. Let us first look at what happens to derivatives. Let's go, forget about Navier-Stokes equations for the moment. Let's just talk about scalars. And let's just talk about, excuse me, not scalars. Let's talk about functions, f of x. Okay, and we already defined a reflection operator on functions f of x like this. We just go fetch the argument over there. Okay, so everybody can see what that means. Now, what happens to derivatives under those circumstances? The kappa f, its derivative is minus the derivative of the original function at minus x. The second derivative is the second derivative. Okay, and let us show this. For this we need to define, it'll be easier if we give a name to kappa f tilde, which is f of minus x. Now let's get the derivative of f tilde. Okay, well we know how to take the derivatives. We take f tilde of x plus delta x minus f tilde of x over delta x. Right, that's the derivative is. Now let's remember that f tilde, what is f tilde? It is f of minus x. So let's do that, where we have x plus delta x with a tilde. We're just going to do minus x minus delta x without the tilde. And here we're going to have minus f of minus x. Okay? So now we just redefine delta x, because this is not how we usually write our definition of derivatives. We'll just define a new delta x, which is minus delta x. It doesn't matter what we call it. So we have a minus. Our new delta x is minus the old delta x, so this guy becomes minus delta x, and this one becomes plus. So here we have the derivative of f at the point minus x. But we have a minus sign from this, and that gives us a minus. Okay? Notice there was no minus in front of this f, but there is now a minus in front of the derivative. But this makes sense. We see it here. We see that the derivative here, okay, when we have the derivative, let's see, the derivative here is negative. And we don't say, let's go fetch the corresponding derivative here. No, that's minus the derivative here. The value of this red function is the value of this blue function at this place. But the derivative of this red function is minus the derivative of this blue function at that place. Okay, and that is the graphical, the way of writing this in symbols is over here with this equation. And that's reflecting the fact that this slope becomes this slope. The values are gotten from over here, but the slope is gotten with a minus. You can, I think, easily see that this process alternates, and so that the second derivative doesn't change sign, just like the value doesn't change sign. Okay, I think if you thought about the second derivative, I don't know. Okay? Okay, so we need that to go to Navier-Stokes. Woo! So we can define, there's a lot of definition, define the Navier-Stokes operator on a two-dimensional vector field uv of xy. Okay? And we know what the, how many people some people here don't do fluid mechanics maybe? I mean, do people recognize this here as the right-hand side of the 2D Navier-Stokes equations? Okay. If not, just take my word for it, but this is what Navier-Stokes equation is. This is the right-hand side of Navier-Stokes. Is that du dt equals this equation, and dv dt equals that right-hand side. Okay? So this is just Navier-Stokes. There's nothing about reflection symmetry or anything. Okay? This is, I'm just setting up notation for Navier-Stokes. Okay? Now, I'm going to have a kappa operator, and this kappa operator, it's the one defined in the very first slide. It's the one that just to be applied. This is x reflection, in the x direction, on a 2D vector field uv of xy. And let's recall we did this over here. We switch the sign of x and we switch the sign of u. And we leave y alone and we leave v alone. Okay, everybody remember this? Okay, so we go back here, and that's what we're defining over here. We switch the sign of u, we switch the sign of x. Okay? Now we want to see whether this operator here, which I call Navier-Stokes on UV, commutes with kappa or not. Okay, so I've written Navier-Stokes kappa is the same as kappa on Navier-Stokes? I don't know. Let's see. Okay, so one direction is very easy to take. We're just going to take this thing here. We're going to do minus on the top. We're going to take, that is to say, let's do kappa on this. Kappa on this. What does kappa tell you to do? It tells you to make my x minus x, okay? And it tells me to make this whole top thing minus. So that's what I've done. I've done minus on the whole top thing. You see that minus sign here, and then there's this bracket, square bracket. So I've done minus on the top thing, and I've taken a minus on the x here. Okay, everybody agree I've done that? We don't do anything to y. We do nothing to the second component nor to y. Now, that tells us that's kappa ns. But now, what about ns kappa? Well, what we have to do for ns kappa is to take u to minus u and v to its own self. What happens when we take u to minus u? Well, we get a negative sign. And what happens when we take the derivative? When we take a derivative in x, we have a minus sign. Right? So, so taking Navier-Stokes on uv, we take this, excuse me, no, that we already did. Taking kappa on this, we switch the sign of u, and we switch the sign because of a dx. And then, for this first term, we switch the sign on u again. So we have three sign changes, u, dx, and u. And that's like one sign change. So that's okay. Now what about this next one? We don't switch the sign of v. We don't switch the sign when we have a d by dy. But we do switch the sign on u. So we have one sign change. So this term is okay. It's got one sign change. dx, we change the sign because it's an x derivative. So we're fine with this one. We have a minus dx. A second derivative, we don't change signs on, whether it's x or y. But we do change the sign because of the u. So that gives us that minus sign over here. What about the second one? When we change the sign of u, when we apply kappa, we change the sign on u, we change the sign on dx, but we don't change the sign on v. That's two minus signs, so that's like no minus signs, so we're fine here, we haven't changed that. Anyway, you see how it goes. Every time you have a u and a dx both together, we have no sign change, because the u changes sign and the dx changes sign. Every time we have a v and a dy together, that's no sign change, because the v doesn't change sign and the dy doesn't change sign. So you see that you end up seeing that all this is necessary. You can't just write down any old. If you were to write something like v dx u, that would be wrong. It wouldn't work out. You would be the fact that you have u dx and v dy, these things are necessary from symmetry. This means that you can allow yourself to have a reflection symmetric situation. Otherwise, if you had terms like this would be implying that that the laws of physics, Navier-Stokes is of course a law of physics, had difference between going right and going left. Because that's all that reflection symmetry means. It means that nature doesn't make any distinction between going right and going left. Right? There's nothing special about right or left. Both are equivalent. And the fact that we do not have terms like this, a v with a dx, is a reflection of that. It's not, of course, to get Navier-Stokes equations, one derive, there's many ways of doing it, or all the laws of physics, particle, continuum, this and that, the other thing. But in the end, you cannot have terms like this because they would be implying a difference between right going and left going. Okay. I mean, I have not shown you all that in detail, but I think that's what I've been trying to say. There's a reason these terms are that way. They have to be this way. U has to go with dx, and v has to go with dy. Okay, so Navier-Stokes equations, of course, are reflections. They're the laws of physics. Now, that doesn't mean that every situation is reflection symmetric. I mean, you can have a box that's not a rectangle. Maybe your box is triangular. Then you don't have reflection symmetry. Then left is different from right. Your laws of physics are not going to distinguish between left and right, but your experimental apparatus can certainly not be reflection symmetric. Or you can put a magnetic field on, or you can, turn your thing at an angle, or you can do lots of things to keep your thing from. But the Navier-Stokes equations, which apply everywhere all the time for all fluids, had better be reflection symmetric. Right? And everything that I said about X, of course, applies to Y as well. Okay? So what's going to, in a little square like this, what's going to determine, or a rectangle, what's going to determine whether your problem is reflection symmetric is the boundary conditions. Your boundary conditions are, here I drew a kind of square apparatus so that the shape is okay, but you have boundary conditions with certain values, and you have to have either oddness or evenness of those boundary conditions. Okay, so let's look at, again, we can learn a lot from these little kind of convective thought experiments. Let's have a roll okay, on purpose I didn't make it exactly elliptic because I didn't want to put in more symmetry than needed. Suppose you have a situation with reflection symmetry, you haven't done anything to distinguish between rightwards and leftwards, then, and you have a solution like this, well then, bifurcation theory, God, physics, and so on, tells you that there also exists a solution like this. Right? So you have two solutions, and they have to have equivalent properties. If this one has a certain temperature transfer property, then so does the other one. Right? If this one starts existing at a certain Rayleigh number, well then so does the other one. Everything you can say about this one, you can say about this one also. But of course, you'll have to say it about minus x, and you'll have to switch the directions. Let's take a solution like this. What does kappa do to it? Kappa does nothing to it. Okay. You have not created a new solution here. This is a little like, this is a simpler version of what I said about the sphere. Here, you've done kappa, and you've gotten the same thing. You might say, oh, but what about this situation? Okay, this situation here, if you do kappa to it, again, you get the same thing. So there is no symmetry principle telling you that this is equivalent to this. Hence, okay, again, these are very powerful ideas. Without doing any calculations, without knowing anything about fluid mechanics, without anything, just knowing that this is a symmetric situation, you're going to know that this flow arose from a pitchfork bifurcation, because there are two of them that are equivalent with just the same properties. So the bifurcation diagram, that's to say any property of, as a function of say, the Rayleigh number, excuse me, I don't mean what I mean to say is, the two solutions start existing at the same Rayleigh number, and if you look at the anti-symmetric component, then then they're negatives of one another. Okay. On the other hand, this one, we don't learn that we have two equivalent flows. We might say, well, if we have this one, it's kind of likely that we might have that one, but they're not equivalent. So what we can hypothesize about this one is that it arose from, say, a transcritical bifurcation with a saddle node, say. We would say, yes, there do exist these two, but they're not equivalent. They're different. There's nothing that tells you that they're the same. There might be some other kind of symmetry that tells you that they are the same. In particular, if there were periodic boundary conditions here, then you would learn that they were the same because it would be a phase shift. But that's, if we just have a rectangular box, then these two are not equivalent, and they do not arise from a pitchfork bifurcation. And remember, I repeat, this is all done without any kind of calculation, just thought experiment, just pictures. Okay, so that's reflection. Now we're going to talk about something more interesting, which is, we're not going to go to spheres for the moment, we're going to go just to the plane. We've been talking about reflections. Let us now talk about rotations, and here are some polygons. But perhaps not everybody isn't totally happy here. I feel there's some problems with the previous part because so much is about notation. So much, there's so much to be distinguished between definition, the three horizontal bars, versus equals, right? Any class that kind of relies on, on distinguishing carefully between definitions, quality means that you have to really bend your mind around. But are there questions? Well, questions might help things to progress. Yes, thank
Just
you.
in the next slide, would you please explain
Yes.
again how we could judge that the second two cases are due to the figure below?
Yes, okay, it doesn't necessarily, okay, this one does necessarily correspond
I
to
got
this.
it.
But the second one, we just know that these are different flows. So we don't know that it looks like that exactly. We know that, okay, so we have, we know we have this flow. And we're going to say, and supposing we continued just thinking intuitively, not rigorously, we said, well, if there exists this one, there probably exists one that looks like that too. That's kind of similar. But that's not math. That's just, we're just thinking that. So we say, yeah, okay, there probably exists another one. But I shouldn't draw it the way I just did. Or, it's okay for me to draw it because I didn't draw very well, indeed. This is not supposed, this distance and this distance, say, are different. And if we go further and we say this arose from a bifurcation, arising from a bifurcation means that it's connected to the basic state. There used to be no convection, and then continuously there started to be convection, so that means that both of these are connected to this zero branch. So let's draw them, let's connect it here. And this one here, well, it's kind of, anyway, that's just a way to, this is just a hypothesis. The part that's not a hypothesis is the part that says we have two solutions. No, that we have two solutions and they are different, and they're not the same. Unlike the first one, which are the same, necessarily the same. Okay, was that pretty satisfactory? It's all rather hand-waving there, so that I can understand that it not being totally clear. It's not. This doesn't. You don't really conclude that. You need a lot of additional hypotheses. But let's just say this picture would be inconsistent with this. And this picture would be inconsistent with that. We can just say that. This would be, if these two flows were the same, if they correspond to a diagram like this, then you would know there was some other symmetry that you weren't taking into account. Which is possible. Here you have rising in the middle, and here you have falling in the middle, and are rising and falling the same? Maybe there's something about the physics that tells you that, but so far we have not put that in. Okay, so that finishes reflection, and I'm happy to take any further questions, because that might help. Okay, so now we go on to rotation. Let us take some objects here, a triangle, a square, and a circle. And of course, a triangle does not have rotational symmetry, only a circle has rotational symmetry, but it does have threefold symmetry. If you rotate by 2 pi over 3, you get the triangle again. If you rotate by 4 pi over 3, you get the triangle again. Similarly, the square doesn't have rotational symmetry, but if you rotate by 2 pi over 4, or by twice 2 pi over 4, you get the square again, or 3 times that, right? Everybody agree with that? So here I've drawn a triangle and a square, and these have dots on them, and these don't. What am I trying to say here? Here I have a triangle which is also a reflection symmetric. I can do a reflection about this axis here, the dashed line, and I still get the triangle. Whereas here, if I do around the dashed line, because I've drawn these dots, you see that the dots are not in the same place. If I do a reflection about this line, this dot here will be on below. Right? So I've drawn those dots to distinguish. This situation is, this triangle is symmetric under rotations but not reflections, whereas this triangle is symmetric under both rotations and reflections. And the same thing is true of this square here. Now what about the circle? The circle, of course, I can't really draw dots because that distinguishes special angles. And that's what I'm not, when I go from triangle to square, I do have special angles, but the circle, I don't want to have special angles. But I want to distinguish between something which is reflection symmetric and not. And the way I've done that is I've made this arrow. The arrow is not supposed to be painted on. The idea is that there's clockwise and then there's counterclockwise. And we're distinguishing between those two situations. So this one, perhaps you have a rotating disc. You know that if you rotate, you have a rotating disc, you don't have a dot on it, and you know that if you have a rotating disk and you rotate it by a little bit and then keep it rotating, that'll be the same situation as if you hadn't rotated it. But if you do a reflection on this rotating disk, and it used to be rotating counterclockwise, now it's rotating clockwise. So that's what I mean to imply by this arrow. It's not something that's painted on. It tells you that this circle is not reflection symmetric. So these words all correspond to groups, and those that have had math, but even those who, I think, even if you've had some physics and possibly even engineering, you've seen these names, possibly even in secondary school, possibly. You've seen these groups. Zn is just a group of whole numbers closed. You do 1, 2, 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, right? 2 plus 2 is 4, which is equal to 0, right? Everybody's seen that somewhere. It's elementary groups. Okay, so you can have this with Z2, Z3, Z4. That is to say, Z4 has 4 elements. One of them is the identity. Always for a group you need the identity. And the other 3 elements are rotation by 2 pi over 4, twice 2 pi over 4, 3 times 2 pi over 4. Okay? Everything we've been doing so far is Z2, that was the reflection symmetry, and if we go back to this group table, this is the group table for Z2. We said that this is the group which has one non-identity element, such that if you apply it twice, you get the identity, and so that tells you everything you need to know about it, and that's Z2. And Z3 is rotations by 2 pi over 3, and so on. Now, if you also include the reflections, then you have groups that are called D2, D3, D4. There are twice as many elements in D2, D3, D4 as in Z2, Z3, Z4, because you can reflect or not. Here you don't include any of the reflections. Here you have all the rotations and a reflected version of each of those. Okay, we'll look at that in more detail a little later. The limit, of course, with the angle becoming infinitesimal, where you just have this circle, is called SO2, and this is where you have an infinite number of elements, and they are the rotations by theta, any theta. So you have a whole 2 pi's worth of rotations. O2 is the name of the group that has all those rotations by any theta, and also reflection. And we can, questions? Nope. Okay. We can make a representation of O2 on the plane using complex arithmetic that makes it easier to think about, and you'll see how we use this in just a moment. We take a number, xy, and we're going to write it as x plus iy, and we know how you've all had not complex analysis necessarily, probably not, but you've all done manipulations on the complex plane, and you know that e to the I theta on a point x plus iy rotates it by theta. So that's what's written here. And kappa z, here we're going to, this is how we're going to define a rotation this way on a scalar. And kappa, the reflection, we're going to take to be the complex conjugate, so that takes a point here and puts it there. That's not the only possible thing. We could have changed. So that changes the y, so that's a reflection in this axis. Of course, we could have also defined it to change the x, but it's an arbitrary choice, and there it is. So with these operations, we can do various manipulations on O and learn a little bit about O2. Let's look at kappa s theta. Let's do s theta on z and then kappa. So doing s theta gives us e to the I theta z. Doing kappa on this number tells you take the complex conjugate. We know that the complex conjugate of a product is the product of the complex conjugates, so you get e to the minus I theta and z bar. Now let's do them in the other order. Let's first take kappa and then do s theta. So taking kappa on z gives you z bar. Doing s theta gives you e to the I theta. And you see that these two things are not the same. So this is the first example in this class of a non-commutative group. S theta on kappa is not the same as kappa s theta. kappa on S theta is S minus theta kappa, as it happens. Okay, how do we apply, that's just the plane, but as we did before, you recall that when we had reflections, we talked about, sometimes we talked about numbers, as we did here. That's like our x plus I, y. And sometimes we talked about functions, f of x. Sometimes we applied reflection operators to functions. So supposing we were doing that here, we wanted to apply a rotation to a function. So now we have a function on the disk, and rho I've written as that's supposed to be the radial coordinate. So we're applying a rotation on the function on the disk, and that's going to, a rotation on a function gives us another function. And what function does it give us? Well, it's like what we did over there. It says, let's go find out what that function is at a different value of theta, at the rotated value of theta. So if we had, I can't draw in 3D, but I mean, I guess I need to do W. It means, let's see, supposing we had we have a circle, and then we have, say, a blue patch here, and a not so blue, and not so blue, or something, and a thing like that. That's our W. It is a picture of W. And how do we get our new W? Well, our new W is going to be, okay, this is going to be a rotation by theta naught here. So now my new W, my rotated one, is going to look like this, and then like that, and then a little thing like that, and then a little thing like that. Where each of these, you see this one has been moved down, and this one was moved, oh, that's not very good, is it? This was moved a lot. It was moved down. He was moved from here, and then this one here was moved up to here, and then this one was moved up to there. Right, so that is, I'm applying a rotation to a function. This is a function on the disk, and I get a new function on the disk. And that's what's written over there in those symbols. Now, we're going to do the same kind of thing that we did over here, back when we found that we had to have an even function, we had to have an odd function, we had to this and that. But let's do that. We're doing something now more complicated because it has to do with rotations as well as reflections. So suppose we had something in the plane. We have here something like x dot equals something and y dot equals something. Okay. But we know that x and y live in the plane, right, x, y, and what we want to express is that our evolution of these points respects the rotation symmetry. Instead of writing, it turns out to be better, rather than writing x dot and y dot, to write z dot equals something. That just combines these two. And it turns out, and to write the most general function, you write it like this. That makes it, otherwise you couldn't have, you would have x and y would have to occur in special combinations if this was just f of z. Okay, so this is the most general, this is just equivalent. Anything that we can write this way, we can write this way, I'm telling you. And it turns out to be, the arithmetic turns out to be simpler.